Hi, my name is Terry Uribe, and this is my presentation on projectile motion for Lab 2. So a little bit of introduction to this experiment. The purpose of this lab was to accurately analyze the projectile motion of an object thrown from rest. To do this, we took an observed motion and compared this to two computational models. The first model uh, does not consider drag force and only considers gravitational force. The second model considers the effects of drag force. So for this experiment, our object was a crumpled paper ball, and then our measuring tool for the observed data was Tracker, and then our computational models were done on GlowScript. This lab covers concepts of Newton's second law and the effects of drag force. So this experiment covered the three different fundamental principles. The first one is Newton's second law, which states that the acceleration of an object is dependent on the net force acting upon it and its mass. The second one is the gravitational force, which is the attraction force between all objects that have mass. And then the last one is drag force, which is the resistive force exerted on an object acting opposite to the direction of motion. So this is a video from Tracker of the observed motion. And this data from Tracker was used for our experiment. So from that video and from Tracker, we found our initial position, and then we calculated our initial velocity from this initial position and then position later, and then our total time is 0.4 seconds. So for our first computational model, which only considers gravitational force, we put in the mass of the ball, and then we put in our position, which we found from Tracker, and then our initial velocity, which we also calculated from Tracker. Then our only force is going to be gravity, so we set our b equal to 0, which is our drag. Then for our first time frame, we have 0.04 seconds, which is going to be the total time. And then again, our only force is gravity, so our F net is going to only be gravity. And then we updated our velocity and our position. So taking that data from that computational model and comparing this to our experimental data, we can see that the computational model is slightly below the experimental data. So now taking the computational model, including drag force, the only thing we change here is going to be our drag force and then recalculating our net force, which is done right here. Then you can see that our velocity becomes nonlinear here as opposed to the way it was with our gravitational model. So combining all of the results from each experiment and computational with gravity and drag force are very similar. You can almost not even see the experimental behind the computational. And then you can see that our computational only including gravity is like right below that. So, conclusions: the gravity only model did not accurately predict the motion of the paper because it neglected air resistance. So, our experimental trajectory showed a reduction in horizontal speed different than predicted by the gravity only model. And then, including drag in the model produced more accurate data indicating significance in air resistance. So, our three possible errors: the first one is unaccounted for forces. So, like I mentioned earlier, air resistance was unaccounted for in the first computational model. The object we used was a paper ball, which is not a perfect sphere, so this could affect data collection. And then our video tracker was recorded from an angle, so this could have also impacted data collection. Further questions: which model predicts a terminal velocity? The model with drag predicts a nonlinear velocity, which is our bottom one here, whereas the model with only gravity predicts a linear velocity, and this disregards the terminal velocity. What would happen to the terminal velocity of an object that was initially thrown downward? The terminal velocity would not change due to the fact that terminal velocity is based on the magnitude of drag force being equal to the gravitational force. So, therefore, this would not change, and therefore the terminal velocity would only occur quicker. Thank you.